Hello world, welcome to the podcast of the Keystone Symposia Modeling Viral Infection and Immunity. My name is Aneone and I'm here today with two of the speakers.
I'm Tom Kepler from Boston University, and my current research is on the B-cell response to vaccines, and we use a combination of experimental work looking at human blood samples after vaccination, and a lot of statistical and mathematical modeling as well, trying to maximize the amount of information that we get from each precious sample.
My name is Katia Koelle. I'm in the Department of Biology at Duke University, and I'm generally an infectious disease modeler and background in evolutionary biology, and I'm interested in the evolutionary dynamics of RNA viruses, both within hosts as well as between hosts, and how that facilitates their spread.
So what was the motivation to attend this conference?
The motivation was, well, first an invitation to, and then the topic of the conference was very much in line with kind of my research interests, so modeling viral dynamics. And it was also an opportunity to, I think, learn about other pathogens that I don't directly study. So I don't study HIV, for example. I study primarily flu and dengue, and so it was an opportunity to see where the developments were going in other pathogens as well.
Well, I came for many of the same reasons that Katia did, but for me it was actually a little bit more than that. I came to help celebrate, frankly, the advancement of computational immunology and virology over the past 25 years. To me, it's really extraordinary to see how things have changed from a very small group of people doing ordinary differential equations modeling using a kind of ecological perspective to what we saw during these last few days. It's just extraordinary, the diversity of modeling, and what's most impressive to me is the number of mathematicians and modelers who are participating in some of the most important biomedical questions that we face today. It's just amazing.
And to go along with that, I think compared to even 10 years ago, I think we see much more data in these types of talks, and then we also see a much more elegant, I think, interface with data. So interfacing models with data, both kind of formally in terms of statistically, and that's been really refreshing, I think.
Can you tell us a bit more about the history of the field?
Oh, well, that may be a bit above my pay grade, but I'll try to give you what I do know. So the first person that I know of that did mathematical modeling of the immune response in the United States, there were several people who did it primarily in Eastern Europe, but George Bell at Los Alamos National Labs started it as far as this history is concerned, and he started off doing, as I say, ecological type models looking at population growth and decline of lymphocytes, B cells and T cells, and that tradition passed then to Alan Perelson, and at the end of the 80s and beginning of the 90s, he really started to educate a huge number of people. And I would say that, I don't know if it's quite a majority, but I think a very large number of participants here are descendants of Alan in the academic sense. But even then, it was still largely modeling in the absence of data and trying to struggle with some ideas, some theoretical ideas. One of them, frankly, was the idiotypic network idea, which was put forth by Niels Jerne, and which really caught the attention of mathematicians. And we spent a long time trying to resolve some of those questions. But the real breakthrough came with HIV, and with Alan Perelson and Martin Novak, essentially a simultaneous publication of papers looking at the dynamics of target T cells when strong antiretroviral therapy was introduced. And what came out of that was twofold. The important lesson for biology was that the HIV virus, even HIV, even during the phase of the infection in which the virus appears to be dormant and the patients are asymptomatic, the virus is replicating at exceedingly high rates. And so it's a matter of an equilibrium where you have very high replication rates and rapid clearance. And this changed the way we thought about the virus entirely. The other important impact that had was on the mathematical community, because Alan used a very simple model, not simpler than it needed to be, but it was certainly simpler than the models that we'd all been trying to put together, and he applied it to real data. And that, I think, really broke the mold and started people down this, what I think has been an extremely productive direction. And from then, I can't repeat the history because I was too busy participating in it.
That's very interesting. But you also mentioned the use of data. So what do you feel about big data coming into this field?
Well, so there's big data, and then there's big data in a different sense. And so I actually had strayed away from doing immunological modeling for a long time and did many other things, including writing a paper with Katia. So I worked in a number of different areas, and I came back precisely because of the promise of big data. When immunoglobulin repertoire sequencing was demonstrated for the first time by Steve Quake on zebrafish, I knew that big things were going to be happening, and that we were going to be able to disentangle some of the questions that had persisted for many years over the nature of affinity maturation in B cells and as a result of vaccination, among other things. And that combined with some of the single cell isolation techniques and recombinant synthesis of antibodies, these things were a siren song that I couldn't resist. I got back into it. And so in that sense, big data, it's not big in the sense that the people who actually study big data think of it, but for me it was enormous, and it really pulled me back in. Nowadays, when I go to my colleagues who genuinely study big data as computer scientists, and they say, we should work together, and I said, I've got 10,000 sequences, and they say, did you say 10,000? Because as soon as you have 10 billion, you can come talk to me. But for me, data, the size of the data is really not that important. A bit of data in a spreadsheet means something very different than that same bit, depending on where the data came from. So if the data are highly reliable and taken under very controlled conditions, it means something a lot more than if you're just trolling for internet traffic, something like that. So our data are big in the sense that they are rich, maybe not quite as voluminous, but I think that's really where the field is going.
Katia, what's your opinion on big data, but also on uncertainty on data?
So I was going to actually speak to you a little bit what Tom was saying before in terms of big data. So much of this morning's session was actually focused on big data in the context of looking at antibodies and affinity maturation, and so more on the host side. But I think there's also been kind of this big data more in terms of sequences, very much on the viral, on the virus side, and I think that has over the last few years really allowed us to really get access to certain questions that we wouldn't have otherwise without those sequence data of the viruses, and so that's both at the kind of the within host level, things like when does antiviral resistance development, for example. It also helps us get at questions that are more between host. So we can look at, by sequencing the viral population, deep sequencing the viral population in donors and recipients of, let's say, flu infections, we can get at what's the size of the transmission bottleneck. We can, and this has been done many times over in literature, is now using sequences to viral sequences to try to determine the network of transmission. And I think, I mean, those data would have, or those questions wouldn't have been able to be addressed as effectively without just, this massive amount of viral sequence data we have now. And it would have been much more, those questions, if they could have been addressed, would have been addressed with data that would have been much more costly to actually collect. Things like contact tracing and diary studies and so forth. So I think viral sequence data have really pushed the field forward in terms of understanding viral dynamics.
All right, thank you for sharing your views. What are your highlights of the day or the highlights of the conference? Things which have interested you during this conference?
Well, so the whole thing is a highlight in a sense for the reasons that I've already described, because it's just amazing to me to see how far the field has gone and how much it is contributing to modern biomedical science. A couple of things stand out for me, largely because of my own interests and because of the novelty of the approaches that are taken. And I'll mention specifically a talk that Thomas Hofer gave on studying differentiation from individual cells. I think that's a really important area, both within immunology and more broadly as well. And the techniques that he's using are just really beautiful, and the methods that he's using for their analysis are. I'm going to read up on those because they're really very nice, and I'd like to make those part of my toolbox. It's also because there's recently, well, it's not even that recent anymore, but regenerative medicine is now focused on making all of the cells that we need for biomedical remediation from stem cells. And so the kind of work that he described is, I think, going to be really important, looking at stem cells and the generation of stem cells, and will guide further efforts to push cells in one direction or another to make them do what we want them to do. So it's certainly not the only talk that I enjoyed, but it's the one that really sticks out in my mind at this point.
I think one of my favorite sessions was, I guess it was on Tuesday morning, which was largely about HIV, latently infected cells with HIV, and then trying to understand, following treatment interruption, for example, when HIV would reappear, and what are these barriers to a cure. So I really enjoyed that session, even though I don't work directly on HIV. And to tell you the truth, I have been enjoying the poster sessions quite a bit, and it's been really exciting to see, I guess, more junior scientists actually presenting such fantastic work, and so that's been really wonderful.
Oh, I agree entirely on both parts. So the idea of trying to cure HIV has recently risen up to prominence, with vaccines against HIV having a longer road and not bearing the kind of fruit that we were hoping for. Mm-hmm. The focus has come to the cure, and that's what I mean by these modelers really being at the forefront. Thinking of cures has only been, I would say, in the forefront for, 2 or 3 years at the most. And these guys are out there developing models that I think are going to be really helpful. Mm-hmm. And similarly with the poster sessions, it's really enjoyable. And these young people are so smart and so enthusiastic and energetic that it really keeps my hopes for science alive. It's easy to get a little bit pessimistic when you've been doing it for decades or more. And it's great to go back and see these young people who haven't become jaded just yet. And so I think we're going to be in good hands for a little while longer.
So what kind of skills or toolbox do you want young people to develop? Oh,
well, so if they're going to follow in the footsteps that Katia and I and many others have laid out, they'll want to understand biology very thoroughly, and more importantly, they'll have to understand how the data are made. That's one of the things that I think that I lacked when I first got into this field, was I would, people would give me data and I would say, great, and I'd start fitting it, but it didn't occur to me to really question where they came from and to understand really deeply. And so I think that technology is playing such a major role now that people who are working in this field have to understand where the data came from, to be aware of the shortcomings of the data, the strengths and the weaknesses. And I think that they, my own point of view, and here my bias shows, is that I think that they need to understand statistics particularly well. I think they need to understand how the real world interfaces with the mathematical world, and I think statistics knows how to do that pretty well.
Those are all good points. I feel like the tradition was people who were trained in mathematics would go then ask these biological questions, and a lot of people from physics, for example, would enter kind of this field, and I think part of it was kind of this appreciation that doing quantitative things was hard and that biology was easy. But I think more and more now, I think there's people who are trained biologically, and are really focused on answering these questions and see the benefit now of models and are training themselves kind of quantitatively, so from that direction, and I think the work coming from people who have had that order of training has been fantastic. And so I again kind of think part of that has to do with reliance on data and how can you interpret the data, and so having really good grounding in that. I mean, I'm a theoretician, and I work with experimentalists, and that's been really wonderful. But I wish if I had infinite amount of time, I would love to actually spend more time or any time in a wet lab actually trying to run experiments
Well,
myself.
So I'll step in and say, although Katia is a theoretician, she doesn't lack for a deep understanding of the biology
Thank you.
that she
I'm
studies.
I'm a biologist.
Yeah, right. She's a theoretical biologist,
biologist.
right? And so I don't think that it's a deficit that she doesn't do her own bench work. I think that the deep understanding of the biology is the key.
But what is really nice is that I think with a lot of these young scientists at the poster sessions, they have been trained both in more quantitative modeling, and then they also have had at least some experience with doing more experimental work or generating data. So that's been really refreshing to see, because you see, I think there has been a tendency for that to increase, and I think that's really positive for the field.
Yes, I believe that nowadays the training is focusing on giving those skills to junior researcher. So do you think that in order to face future challenge, the expectation are higher for the training of young researcher?
Oh, I absolutely think so. I think that the expectations they are now that young researchers will be expert in biology and quantitative science. There's sort of no compromise here. You don't say, oh, well, you don't need to know that math because you're not. No, it's like you have to have a full background in the quantitative sciences and the biological sciences. Used to get away with one or the other, but now to be in this field, you have to have both and be very good at both.
So can you share some practical things that you did in your own case?
Well, I'll say something that may bring on a lot of scorn from the social media, but for me, what was important. So I'm a sort of a classic case that we were talking about earlier. I'm trained as a physicist, and by the time I got my PhD in physics, I literally had not had any biology classes in high school or college or graduate school, but I immediately wanted to do biology, and I brought a set of skills that were very useful to do the quantitative work. But I have to say that it wasn't until I stopped thinking like a physicist and started thinking more like a biologist that I really started to feel like I was making progress. So I had very valuable experience and valuable tools, but the mindset of the physicist is very different. And I think that in the end, the physicist has to give up on the notion of clean, neat little Occam's razor type models and realize that the biological world is really big and really messy and really complicated.
On that point, what will be the ideal mindset for this field of theoretical biology, mixing mathematical skills, statistics, immunology? If you have to lay out ideal mindsets for people, for junior scientists in these fields, what would be the main bullet points?
Well, I agree that it's complicated, but I also think that you can't effectively understand those complicated patterns unless you have relatively simple models, right? So I think so there's always going to. I mean, modeling is always kind of an abstraction from reality, you know. And I think people ask, well, you know, how do you know your model is right? And of course, it's never right. But I think it depends on the question being asked, right? And which abstractions that you're okay making in the context of whatever is your main question you're trying to address. So I think, again, you know, modeling is more of an art and a science, you know, and I think having kind of firm grounding in the biology of a system, you know, and the question really that you want to address, I think is really critical for kind of model design and the level of complexity and kind of what you can brush under the rug.
Lastly, can you say a few words to motivate young researchers?
Yeah, I mean, so two things. First is just that science is a really wonderful place to be. In spite of my claims of being pessimistic and jaded, I can't imagine anything else that I would rather do. Mm-hmm. So I think that we all have an ideal vision of science, and even when it falls short, it's still better than anything else I can imagine doing. The other thing is much more practical, and it's news that I just heard today. And one good piece one thing that should encourage young investigators is that the NIH just released news today that they are going to start limiting the amount of grant funding that goes to people who get a lot of funding already, especially people who've been doing it for a while. And I'm sure I can think of somebody in that category if I think hard enough. But they are going to save money to specifically support younger scientists getting their first grants. And I think that's just fabulous news. And I think that they should all be encouraged by that, that the NIH is really behind them and wants science to grow with the influx of new ideas and new talent. So it's a great time to be a young scientist.
So I think the one piece of advice I would have, so I agree with Tom with you know, science being a wonderful place to you know, for your career. You know, I think it's just amazing, kind of, especially how these viral infections can do what they do in such a small genome. It's always just mind-blowing to me. But I think the one piece of advice I would give would be, you know, to not hold on too tenaciously to your ideas, because I feel like a lot of the times with modeling, you know, you have this model that you know, as you're kind of your baby, you know, you think that that's what's going on, and, you know, especially through kind of an interface with data, you're trying to put this square peg in the round hole and trying to make it work, and then if you just kind of, you know, let go of kind of that being the model, you know, and just let the data tell you something, you know, you're going to be able to find things which you didn't expect, and it's the unexpected, which is really, you know, probably the most satisfying part of this career.
Well said. That's exactly right.
We're going to have this as the last note of this podcast. Thank you very much for your participation, and enjoy the rest of the conference.
Thanks very much.
Thank you.